that uses this algorithm to solve a little problem, just to show the capabilities of these kinds of devices. So first things first, the big question is, what is quantum computing? So quantum computing is basically using a technology that takes advantage of the rules of quantum mechanics and the strange quantum phenomena to solve problems in a different way than a classical computer can do. In some cases, not for every problem, but for some cases, this solution can be faster and more efficiently than in any classical computer. So just to make a brief introduction of the key concepts of quantum computing, this type of devices and technology allows us to perform new algorithms that are different and solve problems in a different way than a classical computer. Due to that it's quantum in and of itself, it's actually quite better for simulating quantum systems and measuring its properties directly instead of making really complex and hard scaling simulations or computations. This kind of technology is implementable in many different systems, such as photons or superconducting circuits or ultra-cold atoms, so it's quite versatile. And it's also compatible with classical computing. So as I said before, it's not better for every problem, it's better for some problems. So just like a GPU can solve some problems better than a CPU, a quantum computer can solve problems in a better way. So it's compatible, and it will just add new assets to a classical HPC sensor. Lastly, I would like to point out that there are many different ways to perform quantum computing or to use a quantum system to solve a problem. And today, the kind of way I would like to talk about is called the circuit model, which is also one of the most extended models and ways to do quantum computing. So here you can see what a quantum circuit looks like. It's actually quite similar to what a classical logical computer looks like and does. Here we can see at the left our unit of information, which in classical computing would be just classical bits, ones and zeros. And then we can see just a succession of operations that we can apply to our units of information to transform them and finally measure them to obtain a solution to our problem. Now we just have to put a nice hat to all of that and turn it quantum. And now instead of classical bits, our basic unit of quantum information is the qubit, which is any two-level quantum system, just like the polarization of a photon, or the levels of an atom, or maybe the spin of a crystal. And then we perform a series of operations to those qubits. We manipulate them using quantum gates. Here we can see an example of a 1 qubit quantum gate, which is basically a rotation and unitary operation on the qubit, and 2 qubit gate, which instead of just acting on 1, acts on 2 qubits, and it's fundamental. So we can ensure that our quantum computer is actually capable of performing any problem. Finally, we have to measure our system to turn this quantum information into classical information our computers can process and have measure different quantities and have an outcome of our problem. So just a bit of a summary. Mathematically, we have an initial quantum state, which would correspond to the ground state of our system. And then we take a unitary evolution of our system until we arrive to the desired state, then measure that state and process the information. These gates are, as I said, unitary operators, and then we can measure it and post-process it to obtain the results we want. I'm sure many of you may have heard of all the crazy applications that quantum computers can have, like solve the protein folding, or simulating super complex molecules or decrypting messages. But those kinds of applications require really large quantum computers that actually can perform operations for a really long time, and then are resilient to errors. So it requires also error correction. So instead of giving you a big list of all those applications, I'm going to tell you about what a quantum computer can do today. So we are today in what's called the NISQ era. NISQ stands for Noisy Intermediate Scale Quantum. So noisy because we don't have the quantum error correction we need. Intermediate scale because we only can control a few qubits, so in the order of the tens of qubits. And quantum, well, because it's quantum, right? So we can just solve small systems and applications that can tolerate errors, so that the quantum errors do not completely destroy our results. And I want to talk to you about two interesting applications. The first one is quite obvious. It's the use a quantum system to generate random numbers. Here you have a picture in which we have a photon with polarization that would be in a superposition of vertical and horizontal, for instance. And then we can use a crystal to separate the two polarizations. And every time one of the detectors makes a click, we can associate that to a bit, so a 0 or a 1. So in this way, we can have random numbers that are way better than anything that we could achieve with a classical system that in the end is just a pseudo-random number generator. So this is really useful for something like a Monte Carlo method that requires not only random numbers, but a really large amount of random numbers that are actually random. The second reason for quantum random number generators is to use them to produce cryptographic keys that ensure more secure communications. And the second application, and which is the one we'll be seeing in more depth, are variational and hybrid algorithms. These kinds of algorithms combine quantum and classical resources. So we have a part that runs in a quantum on a quantum device, and another part that runs on a classical device. And this combination and iteration can mitigate the impact of individual errors in the quantum part of the algorithm. The one I would like to talk about is called the variational quantum eigensolver. This algorithm aims to find the smallest eigenvalue of a Hermitian operator. So as any Hamiltonian that we want to solve, this kind of algorithm can find its ground state. It does it by with three different distinct parts. First, we need to create a parameterized quantum circuit, so a quantum circuit in which we can control and fine-tune the effect and duration of the gates on our system, so we can produce a family of quantum states, of wave functions that will act as a trial function for the second part of our algorithm, which is to measure that state and compute the state's energy or whatever quantity we're interested in obtaining and minimizing. And then we use the energy we measure using quantum hardware as a cost function for a classical optimizer. This optimizer can then update the parameters and the effect of the gates, so we can search a small subset of the Hilbert space, and we can make different trial functions and iterate until we find the smallest eigenvalue of our system and effectively solve the problem. It's really important to note that, as I mentioned before, this is a hybrid and variational algorithm. It has these first two parts. in which we produce a quantum state and then measure it, which are happening in a quantum computer. And this will be way more effective than simulating it in a classical computer, because the size of our problem grows exponentially as we add more and more qubits. And then the second part of the algorithm is classical. It's just a classical optimization problem, which uses what we measure in the quantum device as a cost function. And there are many, really, a lot of applications to these algorithms. The first and most obvious is to simulate quantum system directly and measuring its properties more efficiently in quantum hardware that we could do by simulating it numerically in a classical computer. This can be used to obtain the ground state energy and the ground state wave function of hard-to-solve Hamiltonians in a classical computer. And a really interesting application is that we can encode really hard problems, so NP problems, into problems that are easy to solve by a quantum computer but will be hard to solve for a classical computer. And with that, we're going to start the hands-on. I'm going to show you how to code the VQE algorithm using the Kibo library, which is a middleware library that allows you to simulate and run quantum circuits. And then we're going to use this to find the equilibrium distance of a hydrogen molecule. So it's quite a small system. First, what we're going to do is to build the molecule using the KiboChem library, and then use a Hartree-Fock method to obtain the energy and build an effective Hamiltonian using the 1 and 2 body integrals. Then we will construct a parametrized circuit to produce different trial wave function and use the built-in VQE algorithm to obtain the energy. And finally, to find the equilibrium distance, we will iterate through different interatomic distances to find the one which has less energy. Okay, so before we start, are there any questions about quantum computing or what we are planning to do? Okay, in the chat, Ismail has sent a link to the notebook we're going to be using. It has some text already coded and some blanks that you can fill in to finish the code. Okay, so I'm gonna share my screen again. You can see my screen, right? Okay. So here I'm gonna use, yes, sorry, a bit bigger, and okay. So we're gonna activate the environment that we created before and open a notebook. Notebooks are usually the way to go for small quantum system and small and small circuits. So here we have the step-by-step process on how to solve this problem. So first, we import all of the important libraries we need. Basically, we import the VQE algorithm from Kibo, and we import some parts of the KiboChem plugin, and then just Matplotlib and NumPy for visualization. So what we need to do first is build the hydrogen molecule, and this is really similar to what libraries like the one by Google do. You just need to create the molecule by giving it all of the particles you want, all the atoms you want, and their coordinates. And we're just going to create the hydrogen molecule at a distance of 0.74, which is approximately the tabulated distance for the equilibrium distance for the hydrogen molecule. Oops, of course, I forgot to molecule. Okay, so there seems to be a bit of a problem. Let me check. It would be a hands-on if there weren't some problems, right? Yes. Okay. Now we'll get there, I promise. I think it's here, right? No? Damn it. Okay, yes. Here and here. Nice, we did it. Okay. So what we did here is to build a molecule and then run the Hartree-Fock method. This returns the Hartree-Fock energy. This will be useful later to compare these results to what we obtain using a quantum computer. Now, what we do is build the Hamiltonian. We will try to minimize using the VQE algorithm. Here you can find a more detailed explanation of what this does, but basically what we're doing is computing the 1 and 2 body integrals and building a second quantization Hamiltonian, and then translating that Hamiltonian into something that qubits understand using something called the Jordan-Wigner transformation. But this quantum computer, this Kibo, just manages to do it all for you by with using this command. We are asking to build a Hamiltonian, and we ask it for it to be symbolic. Here, now we can print it and show what we're going to be sending to the simulation of the quantum computer. Okay, it's taking a bit longer than I expected, but we'll get there. Okay, there we go. So here, basically, what we're saying, what it's saying is that it has chosen the CPU to run the simulation, because right now we're not going to use an actual quantum computer. We're just going to simulate the circuit. This right here is the pseudo or effective Hamiltonian of our system that we will be minimizing. Okay. Next, we need to construct the ansatz, which is the parameterized quantum circuit. And we need to define a few parameters. First, we need to say how many qubits our circuit will have, and that depends on the size of the Hamiltonian. Here, in any of the terms, we can see there are 4 terms. So that's the number of qubits we're going to need, which is 4. And then we can say how many times we want to repeat the same ansatz, and that's just going to be 1 because this system is small enough. And then we're just going to use a type of circuit that's already predefined that is called a hardware efficient ansatz that basically uses the gates that are natively implemented in the system, which are just rotations and the controlled Z gate. So this is going to be the hardware efficient circuit with n qubits equal n qubits, and the number of layers is going to be n layers. Okay, and here we can draw the circuit. Here we can see all of the gates that are acting on our system. These are rotation of the single qubits around the Y and Z axis. And these are the control gates, which are the 2 qubits that basically what they do is create entanglement. So we have more expressive circuit, and then we can explore a larger portion of the Hilbert space. And finally, we're gonna construct our VQE object, in which we need to say which circuit will be serving as our ansatz and which Hamiltonian, which matrix we wish to minimize. We need to tell the algorithm which are going to be the initial parameters for these gates, so they can start the search, which they're just going to be random numbers. As we can see, we're going to have 2 times the number of qubits, number of parameters. And our solution will be to minimize the energy of the Hamiltonian. And there's minimize. No, yes. No, there's an unmatched. Oh, here. And qubits. Oh, yes, sorry. Just missing a bit of character. And we're done. Here you can see that the VQE algorithm is completed. This is the final obtained value of the energy. And this is the parameters that produce this state. So now we not only have the energy, but we can reproduce the state just by inserting these parameters into the circuit, and we can make more measurements or more computations to study the ground state. And now here we just do this all over again, just looping for different distances and seeing which are which is the equilibrium distance by minimizing. So let me just copy this so we don't have the same problem again. Here, I want to place the first atom at the 0 and the second at distance t. Then we run the Hartree-Fock, create the Hamiltonian, and minimize and construct the VQE object, and then finally minimize. And the solution will be the initial state, just the random parameters. We can also specify which method we wish to use for the minimization. This is any SciPy minimization method. And then this is going to take a few seconds as this loops for every distance we demanded. We can find the equilibrium distance, which is 0.71 Armstrong, which is quite close to the actual result. And the equilibrium distance, the equilibrium energy, which is, as I said before, really similar. These are the same results we will obtain using a Hartree-Fock method. So this is the Hartree-Fock energy. As we can see, is basically the same result. And now, just to illustrate the result, creating this plot that shows the ground state energy as a function of the intermolecular distance. And here we have a zoom between the 0.2 and 1 range. And this is the equilibrium distance, which coincides with the minimum. And that's going to be all for the hands-on, just a way of showing that quantum computers can be used to solve many different problems in different ways that a classical computer does. So if there are any questions, I'll be glad to answer them. Any suggestions too?
Well, if there are no questions, that training session ends here. We want to thank all the attendants for being here, and we hope that you find the session interesting for you and your work.